Great. So everyone had a wonderful lunch, and our first speaker this afternoon is Zoran Grujić, who will speak to us on criticality for Navier-Stokes.
Okay, so yeah, so it's let's see what happens. Yeah, so happy Cinco de Mayo, right? Maybe that's good. Okay, yeah, well, all right. So I'm gonna basically talk a little bit about some method that the idea is to actually not use normal interpolation, right? Because if you interpolate lower order terms, then nothing happens. So you want to interpolate differently, and then the idea is to look at some monotonicity of sequences of derivatives, increasing, decreasing, and use that instead of interpolation to basically estimate the lower order terms. And then, of course, there is space in between when you cannot do it. So you cannot divide flow in two parts when you have this monotonicity of parts of derivatives and the rest. And then you kind of need to apply two different methods basically to treat each scenario. And this is about the first thing that basically when higher order fluctuations dominate lower order fluctuations, which is what we call turbulent scenario. It's kind of right. I mean, some sort of higher order versions of the, Taylor scale, if you wish, small, right? Okay. Yeah, okay. So, well, all right. So just like a little bit of standard numerology, right? So, well, let's see, let me just go back. So yeah, so we have this hyperdiffusion exponent beta, right? That you're gonna look at, we're gonna look at the hyperdissipative case, so it's beta is greater than 1, and there is no external force and viscosity is set 1, so and there is no boundary, there is nothing, just R3, right? Pre-equation in R3. Yeah, okay, so yeah, so we know, since Lyon's, that if beta is greater or equal than 5 quarters, there is no singularities. Obviously, that's where energy level and scaling invariant levels meet. So we can use lots of classical PD techniques, and that works fine. And then in supercritical regime, basically, right, we have results that are pre-scaled versions of the Navier-Stokes results, right? I mean, it's basically okay. Sometimes if you do local theory, it's a little harder because you have to localize, fractional powers, but one can do that. So at the end of the day, it comes out the same pretty much. Okay, and then yeah, so that's one of the reasons that we sort of are afraid even more maybe that we should be of the Navier-Stokes, because there is this clear gap between 1 and 5 quarters. And also, so in particular, this is what I kind of want to show as a test of this theory. If you look at these rescaled families of profiles, right, kind of generalized versions of how one would look for some similar block, but you allow parameters to go anywhere in the supercritical regime too. If you make a little LP diagram, right, it's again also just a rescaled version of the Navier-Stokes diagram. And well, let me show you actually the right. So basically the standard trick laboratory for scaling things to see. You have these two parameters alpha x and alpha t, and then try to do your scaling. Yeah, we are gonna basically have lower and upper bounds on profiles, right? So that the actual dynamics is really totally driven by these two scaling exponents. So I mean, it's easier and it's more transparent, right? What happens? And so basically, okay. So let me show you this, I guess. Right, so this is, so beta is between, say, 1 and 5 quarters. I mean, you can plug in 1 and then you get the Navier-Stokes diagram, right? So if you do that, then, so the shaded region is the thing that it's, we cannot rule out by classical theory, basically. So if you take, say, beta equal 1, right? If you look at these two main lines, right? Alpha t is 3 alpha x, that's just finite energy. Well, that's the same. But that's not going to get different for hyperdiffusion anyway. So that one will stay the same. And then the next line is this criticality line. It will be L3, L infinity 0 t, L3 for the Navier-Stokes, and that's the appropriate line for the hyperdissipative, right? I mean, this here, right? So this is finite energy. This is scaling invariant level, and then this is just type 1 blow up. So you can cut that off. And so if you are, one can do other things, but then if you have actually finite, if you have energy inequality, right, then you have this line for the integrability of the gradient, and then you get a finite set, right? If you just want to look at L2 finite energy, then this set is actually infinite, right? Set of parameters where you can't really So so this is self-similar profile. We can eliminate that, right? And that's where the type 1 blow-up line and the LP self-similar, I mean, scaling invariant line meet, right? So that's like everything it's critical in all kinds of ways, right? Okay, and so then sort of. Okay, so let's go back. Right. So this is kind of yeah. So what I'd like to basically talk about a little bit that for some scenarios, right, we don't really need to wait until beta is 5 quarters, right? We can show in this particular case here, right, as long as beta is strictly greater than 1, we can cut out like a whole new part of the parameter space, right? And so go into the supercritical regime. Then, if we are sort of, if you stay with the finite energy solution, I mean, if the Leray solutions, right, if you have integrability of the gradient, then there is actually a threshold when we eliminate all these all the rescale profiles, right? So when beta gets to be this, like this line here, wait, yeah. So this line, this line is the, let's see. All right. Well, yeah. Okay. Yeah. So this is the new dividing line here, right? So basically, as long as beta is greater than 1, you go in a little bit, so you shave off a little bit of the supercritical regime. But then if you get 1 plus square root of 2 over 2, right, then this line is actually going to sweep the whole, the whole gray region, and it's going to, right, there is going to be nothing left, right? So there is this, right, so there is this parameter here, right, the value for the beta. Well, hopefully this is less than 5 over 4. Yeah, okay, it's like 1.21 or something, right? All right, so, and this is, yeah, this is joint work with Lyosha, right? Whatever I'm going to present. So okay, so this is one sort of test result that comes from this turbulent dissipation theory that we are kind of looking at. So then, we just wanted some sort of example that one can show something methodology free, right? That how this turbulent regime in the hyperdissipative case, we can really in something concrete get into the supercritical regime. Okay, well, all right. So I mean, this is just description of the lines, but I guess we talked about this, right? So, or maybe right one more time, quick, right? So yeah, this is yeah. So this is just finite energy. This is the critical LP thing and the type 1 blow, right? And the gradient thing, and this is the dividing line that comes from this turbulent condition, right? Okay, right. So this is theorem basically, right? So as long as beta is greater than 1, right, we can cut out a little bit of the supercritical regime, and this is the this is the dividing line, right? Okay, yeah, and then if you are like, yeah, if you sort of don't leave the Leray universe, right, then we can actually eliminate all these rescale profiles tiny bit earlier than 5 quarters, right? That's like, I don't know what this is, 1.12 or something, right? Okay, all right. So that's sort of the result. And now the question, okay, right? So what do you do, right, to get here? Some methodology. So right, so this is kind of based on this. I mean, there are two things, right? There is this base methodology that's kind of sparseness of the regions of intense fluid activity. It could be velocity, it could be vorticity, it could be higher order derivatives, right? Depends what you're interested in. And then you kind of, yeah, you sort of mix this with this dynamics of the, you basically make some order among different levels, different basically orders of derivatives, and you just study monotonicity locally, and so these are like sort of two things that get mixed to produce that. But okay, so let me just start with this general methodology. I'm just going to illustrate this on the case of the vorticity. It's easier to when you have one field and then countably many moving around at the same time, right? So let's just look at the vorticity, right? So basically, okay, so we know that locally in time we have analyticity, we have spatial analyticity, so that's basically our manifestation of the diffusion. And I mean, there is nothing weird here, right? So basically the idea is that obviously fluid concentrates on the regions that are small, right? At some point diffusion will take over and smooth out everything. Is just basic turbulent dissipation. But this is just like, one other, another way to actually measure these things, right? Because we can measure, we get an estimate on the analyticity radius, that's our dissipation scale, and then we need some a priori estimates on how sparse are the regions of intense vorticity. And then if the analyticity radius is larger, then we are good. We can apply a nice maximum principle harmonic measure of the region. So high vorticity is going to be small, and then you get a better maximum principle, and then you can control the growth of the vorticity, the L-infinity norm. So that's basically the whole idea, right? So that's just one way to look at anticipation, basically. Okay, right. So that's sort of the general thing, and then okay, so it turns out that what we need is sparseness that's just one-dimensional, so it's a local thing, right? So if you take a point, you're looking at the regions where vorticity is large, it's going to be super level sets of the vorticity above fraction of the L-infinity norm. And so it's like a local thing, right? At every point, you can choose a different direction. So you just need to have one direction in which you have 1D, you have delta sparseness, right? But then also, right, it's this is hard to get a priori estimate on. So all our a priori estimates are more or less on the 3D sparseness. And then, so I don't need to explain this too much because Anna did already this morning, right? This is a half of this is semi-mixed, right? Basically at the scale, right? If you assume this on S and the complement, then S would be mixed at scale R, right? So this is basically semi-mixedness, right, on the geometric version of the mixing scale. Yeah, so here, yeah, we don't necessarily need to mix things, we just need things to be sparse, right? Because we just want the regions of intense vorticity to be small, right? So diffusion can take over and just smooth it out. So one side is enough, right? We don't need to have actual mixing. Semi-mixed is plenty good for this. Okay, and then of course, like 3D sparseness is going to give us 1D sparseness. You can think about many sets when 1D sparseness is going to work better, obviously. So the thing is that, yeah, what is good is that we just need 1D sparseness, right, to get the regularity results. What's not good is that a priori bounds are all from 3D sparseness. So there is some thing that we've been playing recently. That one can reformulate this 1D sparseness in terms of the directional maximal function, right? Because if you just look at the complement, and then, right, because here it's, you cannot take the opposite statement, right? You just need one direction such that the thing is sparse, and then yeah, you just take just negate this, and then it's for every direction it's not, and then you can introduce directional maximal function, and then you can try to get some smoothing playing with the directional maximal function from there. But if that works, it's going to give logarithmic improvement. It's not going to get power improvement. So if one works for on some sort of critical problem, that might actually help, right? But not for like a super critical thing when difference is algebraic, right? Well, okay, so I just wrote down a couple of propositions here, just technical things. So this is the version of the basically harmonic measure maximum principle we are using. Okay, so this is just upscale version of 3 lines theorem or 3 circles theorems from complex analysis, right? I mean, okay, well, it's a more for the more general thing, but it's the same story, right? Because I mean, this is written for subharmonic function. If you think about version for analytic functions, right? Then log of absolute f would do that, and you get this log convexity. But it's really kind of 3-circle Hadamard theorem in its basic form, right? It's basic interpolation inequality, but then you just make it into a more general setting that you can apply for things that are a bit more general pieces of sets. And then what happens, because we just need 1D sparseness locally, then so basically what it is, it's obviously a 3D flow, right? And then you look at one point, and then in one direction, you have this sparseness of the regions of high vorticity. So what you do, you can translate that, say, point to the origin, you rotate, you make that direction, say, x1 coordinate axis, and then you can forget about the other 2 variables and just look in the complex plane. So you can just take some sort of simple, relatively harmonic measure estimate on the unit disk in the complex plane, right? Because you basically just say, okay, right, so, now I'm at the origin, and I'm say sparse in x1 direction, and now I make complex variable here, And so then, yeah, so you have this scale of sparseness. It's kind of like, okay, well, right. So you basically have this disk in the complex plane. And so this is what it used to be your direction, and so you have some sparseness. So all you need is some sort of estimate like this that will tell you lower bound or upper bound, depends on which side you have. If you have some sort of subset of the segment of, and you can rescale, right? Obviously, this is invariant to any conformal map, so you can just rescale. Oh, yeah. Okay, thank you. Right, so you can just rescale this, and then yeah, so pretend that you can pretend that you're on the unit circle to start with, right? And then you can use this estimate that, basically, okay, it's super, right, intuitive. It says that if you're computing harmonic measure at the origin of some set that's basically a subset of this segment, right, it's going to be greater or equal than if you take the whole set and, split it in half and push to the end, right? So, I mean, this obviously should be the worst case scenario, right? If your set is just pushed to the boundary because, right, there is nothing here. But then surprisingly, this is actually somewhat painful to prove. I mean, Solidin did it, so we don't need to worry about it. But this is kind of like, yeah, it's concrete estimate that we get to use in computations, which when we need to, when you want to actually have quantitative estimates on everything. Okay, so, and then also, well, we need some analyticity, right? So we need some estimate on the analyticity radius. So, in vorticity, it would look something like this. Of course, it's local, right? So you start with something LP, and then analyticity radius expands like square root of T, and then just, make your estimate, depends what space you want to be. And so then this last ingredient, so these things before were for regularity criteria, right? So you prove theorem that says, if the sets where vorticity larger sparse at a certain scale, small enough scale, then you're good, right? Then there is no blow because you can use this sparseness of the sets and the better maximum principle, and that gets you contradiction to the blow. And then the other part of the thing, it's of course, okay, you want to get some a priori sparseness. You look at the sets and you want to be able to show a priori they're sparse. And this is definitely mixing, right? This is actually borrowed from here. Well, okay, so I mean, it's a vectorial version of the scalar thing, but it's a simple duality argument, right? There is, you can prove this in pretty much any space and the dual, right? I mean, you just make a duality argument and you get this. And then, of course, with vectors, things get weird soon and quick. And so the thing is that from condition like this, at least I don't think one can prove sparseness of the full vectorial set, right? So if you look at the super level set in terms of the full vectorial norm, there is no way, it just gets tangled up all the time. But if you take these 6 components, right? So basically plus minus, right? This plus minus is positive and negative part of the function, and it's a vector, right? It has 3 components, or these 6 things that are just scalar functions. Each of these 6 super level sets you can get that they're sparse at a certain scale. And that's all you need really, because, right, you're basically using the maximum principle on subharmonic functions. So you have your vorticity, it's analytic function, right? Components are harmonic, and then you take positive and negative parts, it's subharmonic, and then it works. So you can just do component by component. Which is nice because, yeah, the vectorial super level sets they're not going to be sparse actually in general. So that's nice to that's luck, I suppose. All right, well, okay, so this is not really necessary, but okay, just for notation, it's kind of convenient to look at, maybe codify this in some sort of function class, right? And so you can say, okay, I'm going to have my parameters, right? So alpha is what we really care about. So you're looking at the basically super level sets of each of these 6 components, right? Above fraction of the L infinity norm. And then alpha, so you want this set to be sparse at scale, that's some sort of inverse power of the L infinity norm, right? So this alpha, it's really what we care. And then, okay, so there is lambda and delta, obviously, and right, you just fix them. And I mean, you can play with them a little bit, but right, not really too much. And okay, this is some sort of size parameter, right? And then, so then we call this the alpha classes. Right, and so then, yeah, so then for vorticity, we have these 2 things, right? The regularity class is C1/2, which is basically scale of the analyticity radius, right? And so then one can get that argument with sparseness, 1-dimensional, and right. send things here and use the nice maximum principle. And then the 2/5 comes from a priori bound comes from this lemma, just from basically the fact that L2 norm is finite, right? So you start with some base norm here. Here you will take K is 1 and S is 2, and right. So you basically just assuming that the L2 norm is finite, you're gonna get the exponent is 2/5 here for the vorticity. And so okay, so that's right. So well, one remark is that right. So if you kind of look at the vorticity super level sets, if you look at the kind of the worst case scenario, like a ball, say around the point, right? Then okay, so you know that vorticity is in L1 a priori. Okay, well, L infinity 0 TL1 is the right energy level best a priori bound for vorticity, right? So you're gonna get Z1 TET, right? So, but then, right, if you look at the sparseness of these 6 super level sets with this duality lemma, you get 2/5, right? So at least within this framework, right, this moves a little bit, which is kind of nice. And then, you know, this 1D versus 3D, right? The thing is again, right? I mean, we really don't need 3D sparseness for the regularity criterion. We just need 1D sparseness, but yeah, right. It's hard to get 1D better estimates. I mean, in principle, you can't in the worst case scenario, but then like you cannot do a little bit dynamically and see how things deform, and you could think you can get at least logarithm out of that, but that's some sort of in another 5 years thing. Okay, so yeah, I just want to also show like for vorticity. So this is with collaborators in Denmark some years ago. We were playing with for the KIDA simulation, and then we kind of basically, well, we know what the analyticity radius is, right? It's this, well, broader viscosity back, right? So it's nu to the 1/2 square root of L infinity norm, right? That's our lower bound on the analyticity radius. And then, right, so we would, for us, you know, for this mechanism to kick in, right, the scalar sparseness should be less or equal than that, basically, right? Then the mechanism works. And so we did this with basically computed the actual geometric scalar sparseness, which we call R. So this was kind of, right, so, well, there is some sort of geometric algorithm, you know, it's an algorithm from computational geometry, right, that you can run from your data set and compute the scalar sparseness basically as suitably defined. And then we also, well, this is like, these are computational physicists in Aarhus, they also have this thing that's called Science at Home. That's for popularization of science. So that's pretty good because they designed a video game, and then we had like people playing game and collecting data. And so we had the scalar sparseness both from the game and from the computational algorithm. So it was fun for everybody. But so, okay, so we have these 2 data sets for R and for T, and then we kind of looked at the time slices leading to the peak. And basically, we did the log-log plot. We wanted to see if there is some sort of power law dependence between the actual scalar sparseness and the diffusion scale. And then we got this log-log plot that is basically, okay, the slope is, well, it says there, it's 1.098 something, right? So yeah, just tiny bit above 1, which basically means that the scalar sparseness is a tiny bit smaller than diffusion scale. And that kind of, right, explained why the thing slumped down, because basically the right flow, the regions of intense vorticity got exactly sparse enough for the diffusion to smooth them out using this maximum principle. And so that was kind of fun, right? So because, I mean, all right, so this is not mystery that this doesn't blow up, but, you know, to provide some sort of actual mechanism why that happens, right? Well, yeah, so it's a couple of sines and cosines, so it's like it has like about 6 symmetries, and they're preserved in the flow. So if you look at the super level sets, right, there is still the symmetry is preserved. It's little chunks here and there. Yeah, well, I have one piece of super level set. There it is from the video game. No, but it's really 6 symmetries, and they're just preserved, right?
What's known about the...
Well, this is like, you know, so Kida and Murakami, well, Kida introduced this, and Kida and Murakami were playing with this. It was basically for the purpose of computing more efficiently turbulent flow, because you get sparser computation, obviously, because there are symmetries and it's on periodic cube, right? And so you can use symmetries and things to cut. And then, well, then Boratov and Peltz, right, to look at this as for Euler, right, and also for small viscosity. At the time, they're right, so that they thought perhaps this is a good test for singularity. So, right, they would take smaller and smaller viscosity, get sharper and sharper peaks and things, but things would always come back, obviously, at least for when there were any viscosity. And I think at some point they did also simulations with this guy to just convince more convincing, more modern simulations that. So it's not that right. So it's clearly from different results. There is no singularity here, but at least for Navier-Stokes, probably not for Euler either. But okay, let's not worry about that at this point. Yeah, but it's for us was just okay. There is something that has like it's intermittent enough. There is a strong peak, and just to see how this scale, basically the actual scale of sparseness relates to the analyticity radius to the diffusion scale. That was kind of idea. Okay, yes. So all right. So yeah, people are playing. That's good. Now that was all fun and games, I guess, literally, and now we have to see what to do with these things, right? So basically, okay. So we are gonna look at now u velocity as a base norm, right? And then look at this whole sequence of derivatives. Okay, so this is sort of how things work, right? So if you look at just the same duality lemma, right? And then you're looking at the super level sets of the derivatives of other k. Well, this is the scale of sparseness that you get, basically, right? Okay, then you can just do L infinity estimates to Hamel at the level k and do interpolation normally and complexify the estimates and do all of that. You get some sort of local in time thing. You take 1/2 beta root out of it, right? And then you get analyticity radius, and then that's this. And so that doesn't really look good, and it's not going to do anything because it's the same thing, right? So, think of just for Navier-Stokes, right? Put beta equal 1. I mean, right, there is 1/k plus 3/2 and 3/2 1/k plus 3/2. So everything, it's doing what it's supposed to do, the staying apart for a fixed amount, right? Okay, so that's nothing, right? It's happening. All right, so now this is what we kind of want to do, right? So we are going to look at situations when there are portions of these chains of derivatives when it's either higher order derivatives dominate or lower order derivatives dominate. So there is some sort of monotonicity. And I will show in the next couple of slides on numerology how this comes up. But basically, the monotonicity would give us a much better estimate on the analyticity radius. So as long as you have portions of chain either going up or down, right, either higher or lower order derivatives dominating, this is your analyticity radius estimate. And so this is obviously much better than that. And then it's not only that, is that if you take Navier-Stokes, right, then it values 1. Well, these two things kind of asymptotically converge to each other. But as long as you have any hyperdiffusion beta greater than 1, right? I mean, this is actually gonna get bigger, and so then you're good. You're in business on the left. Okay, so you fix some beta 1 greater than 1 for large enough k that depends on beta, which makes sense, right? If the smaller hyperdiffusion, you need to go to higher level of derivatives to actually something to happen. So yeah, so if one can get analyticity estimate like this, then you're fine, right? Then your analyticity radius for k large enough, it's gonna get bigger than the scale of sparseness, and then you can use this argument, right? Okay, well, so yeah, and then the problem is like when it's obviously flow is not monotone, why would it be, right? So you kind of sort of approach the singular of time and space, and then you kind of have to break your dynamics into monotone and either increasing or decreasing and kind of in undecided parts. And so monotone is really higher order derivatives dominate because lower order derivatives dominate. That's actually easy to I mean, if somebody tells you, okay, here is a nonlinear PD and the lower order derivatives dominate higher order derivatives, you probably wouldn't worry too much. So that part is believable. So that's why I call it turbulent scenario, because it's kind of, higher order fluctuations dominate lower order fluctuations, basically, right? Well, yeah, this undecided part, it's like a totally different method. And, we are working on that, and it's a lot more geometry, and it's much more subtle actually. But in 20 years, show you something hopefully. Okay, let's see how is the monotonicity exactly helping, well, okay, so let's say that do this sort of naive thing that pick some level k, and then let's say that for all levels before you have this, this is just, so that it's dimensional, right? I mean, both of these things are now the dimension of they're proper length scales, right? So, okay, so I assume this like clean monotonicity, for example, right? And then, okay, so then you take your Happer dissipative Navier-Stokes, take derivative of order k, just write down Duhamel, do L infinity thing algorithm, and you're going to get this, right? You're going to get the time of existence exactly that. And this is time space, right? You take beta root to get analyticity radius. So it's exactly this thing that was, sort of promised there, right? So there is no like any super magic, right? I mean, if you take this clean monotonicity, you just do the most standard estimates, you just do it in L infinity, you get some local in time existence, you complexify, you get, right, you take the root for the scale for the length, and then this is analyticity radius, okay, except that there is still, I mean, this is sort of cartoon still, because even in this case, the point is that if one wants to do it, super easy, you would need to assume these estimates in the complex plane, which makes zero sense, right? You cannot estimate, I mean, assume anything in the complexified space. So you need to leave those inequalities up in the dynamically in the complex plane of the real space, right? In the complex space. And so then this K basically needs to be large enough both in terms of beta and also in terms of the L infinity norm or where you start, right? So there is a little bit more, but I mean, this is basically numerology, right? If you have a clean ascending chain, right, you really get this. I mean, this is what comes out from the normal Duhamel and the normal estimates. Okay, and then, yeah, okay, well, right, this is, we sort of talked about this, right? This is the scale of sparseness, and then, yeah, for large enough beta, I mean, for any beta greater than 1, for K large enough, we are going to be all right. Analyticity radius is going to be bigger than the scale of sparseness. So this is for ascending chain, right? And then for descending chain, if you would kind of reverse these inequalities on the top, it's actually quite different argument. What you do, you basically go back to the sort of original set analyticity estimate, that one, and you start there, and then you use that floor order derivatives dominate, and then you just estimate directly Taylor series. Actually, you don't do Duhamel there, right? You just use this is came from Duhamel, but then you improve it by assuming that lower order derivatives dominate, right? You just extend the radius of convergence. It's kind of like analytic continuation of sorts, and then you get this, and it's better because here you don't need beta greater than 1. This works for Navier-Stokes actually, even when beta is equal 1, and you can in descending chain you get a preferred analyticity radius, and I don't think you even need 1. I think if you take any beta greater or equal than a half, so you can just do L infinity algorithm with Duhamel, it would probably still be fine. It's just, all right, so that's kind of if you have this monotone pieces, and this is sort of not super technical, it's clear what's happening, and then what's really technical, it's this, right? Now you sort of have to go and approach a singular time, and then you kind of have to split dynamics locally in these monotone pieces and the rest, right? So when it's kind of derivatives are comparable, and then, right, so then one needs to kind of introduce some sort of order in these chains of derivatives, and you kind of solve locally everything carefully in time, how much time it takes for like type of chain to switch from descending to ascending. So it's very technical, and perhaps can be done a little bit more transparently, I suppose, but that's what one basically does, right? And so then at the end of the day, right, so we have these two scenarios, the turbulent one and the complement. Turbulent one is this when there are monotone pieces of the chains, and we have preferred estimate on the analyticity radius, and we can do stuff. Okay, so this is what comes from, the estimates we have, right? We settle this on definition of the turbulent scenario, right? This is approaching the singular time. So you take some lacunary sequence, right? It doesn't have to be K2K, yeah, just take something, and you have that, right, the higher order derivatives dominate. This clearly, I mean, this is big, which is good because then it gives us more freedom. But yeah, so this is, and it says essentially because there is also quadratic perturbation there. It's not just beta -1, 2k + 1. There is some k square thing, but okay, you can sort of ignore that basically. So essentially, this is what we identify as turbulent scenario, and in that scenario, right, we can show that as long as beta is greater than 1, there is no blow-up basically. Yeah, and so right, so this is for one of, it's enough to assume in one direction, so this could be directional derivatives. So it's locally around the point, right? So you need to have one direction again. The directional derivatives have this property that you can estimate the lower order with higher order, and then you're good, right? And so the other reason, so there is some sort of local anisotropy. It's allowed, right? It's not enforced, but the point is like the opposite scenario then would be that for all directions, derivatives are kind of comparable. And so that's this other scenario that we have. And so then what happens if you think about this, right? If in all the directions around the point, all the derivatives are somehow comparable, you can get some sort of quasi-radial symmetry around that point. And so what happens is then if you have quasi-radial symmetry, if you keep taking derivative, there is going to be sign change. It's going to be almost like sine cosine, right? It's going to be plus, minus. And so when you do your Duhamel for order k, you do Leibniz, right? If you have the Leibniz expansion, derivatives will come with different signs. And then that would actually then introduce cancellations in there. So it's a completely different mechanism than this monotonicity, right? And so that's what you're kind of writing now, but you know, that's going to take a little longer. But that's kind of the idea, right? So here it's enough to have one direction in which the higher order derivatives dominate, and then the other thing, it's all directions that are kind of comparable, and you get some quasi-radial symmetry, and then you can extract different types of cancellations completely out of there. But yeah, so then you know, this is why we kind of look at these rescale things, because okay, one can say, well, all right, so this is just some sort of regularity criterion, fine, like maybe it doesn't do anything different than anything else, but then okay, so right, we just apply it to that ansatz and see what happens, right? I mean, there we can compute explicitly everything. So this is what happens, and now we basically just have to make sure that that right-hand side is less than whatever the condition that in our regularity theorem is that defines turbulent region. Right, and so you do that, and that's how we get that line on the slide. I want to go. I hope. Right, so this is the dividing. Oops, the dividing line, the thing on the bottom, right? That divided the gray regions, the light and the dark one, right? And so basically, yeah. So this is. I think it's nice to see that. Well, let's just go back there 1 second. Probably better way to do this one by one. Yeah. So basically, yeah, so that's our, you know, dividing line that came out from, you know, this being in the turbulent scenario, basically. And then, yeah, it's, I think for me, it's actually the most fun part is that there's some sort of criticality of diffusion, right, at 1, because as long as you move a little bit, I mean, as long as beta is greater than 1, you cut out neighborhood of self-similar profile, right? So if you kind of look, we know the self-similar doesn't blow up, obviously, but now you can actually have a proper neighborhood. You can toggle your exponents, both supercritical, subcritical, wherever you want, and it's kind of like, you know, stable, right? I mean, in the sense that it doesn't blow up, right? And so yeah, so that's pretty much you know, what I wanted to show, right? There is one more slide, I think. Let's see if I can get that. Right, I just like this, you know, like to show this always. Well, it's obviously a study of, like, you know, great wave, but it's not the final version. I like this one better because there are clearly birds doing stuff, and so anyway, this is turbulence. So okay, thank you.